Okay, lab 3 today. So students in column number 3, member 3, basically here are the primary point persons for the first one. So you have Keller, Connor, Roderick, Isabella, and Antonio. You are responsible for coming up here and obtaining the circuits. Either one, it's fine. Either one of you is fine. So you are responsible to come up here, obtain the equipment from the cart, get the cables from the wall. And you will be responsible for the first circuit. Okay, let's bring up the first circuit. Excuse me. All right, so lab 2. Hold on, you know what? And get it directly from here. So you need resistor box number 2, 4, and 5. Okay. If the value of the resistors are slightly off, that is fine. Just let me know, and then you make sure that you note it down in your lab notebooks. Okay. So everybody should have their lab notebooks open. Today's lab is a little bit special because it mimics the dual power supply. So we're going to use 2 power supplies, combine them together, and we're going to use them to verify KCL, KVL, and the superposition principle. Okay. So again, primary point person is going to build circuit number 1, procedure 1, and then you have procedures 2, and there's actually a couple of calculations and multiple tables. Okay. So you got 3 tables in there. You have 3 tables in there, but you have procedures 1 and procedure 2. Okay. Okay. All right, everyone ready? We still got 2 people left. Okay. Anyone ever have experience with the hot tub being installed anywhere? Have you ever heard of people installing a hot tub and needing an electrician to come out to do something? Ever hear of that? Right. So what they are doing is, let's see, let's make this a little bit bigger. Okay, and let me actually go to the lab notebook. All right. The voltage supply that comes into the electrical power connection that comes into our residences is known as a single phase supply. And between the 2 wires, we have voltage that is between 110 to 120 volts between the 2 wires. Okay. Now, something like a hot tub requires a whole lot of power. Right? You have these fancy jets in there. You have this electric pump, the electric water heater. All of that requires a lot of power. Electrical power is given by P equals VI or IV, product of the voltage and the current. So if you wish to increase the power, you have to increase either the voltage or you have to increase the current. Now, increasing the current means you have to have wires or cables that can handle that high amount of current. Okay, there's a lot of cost associated with that. Also, power is I squared times R. Or long distances, R is very large. And the power loss that occurs during transmission is square of the current. So if the current increases, then your received power increases, but at the same time, your losses also increase. And the losses are massive. due to the square of the current. Okay. And so it makes more sense to increase the voltage rather than increasing the current. Okay. So you increase the voltage if you wish to obtain increased power. And the way they do that is you combine two phases together. So this is known as a single phase supply, and electricity is transmitted in multiple phases. Okay. So you take a second phase and you combine it with the first one. And the second phase would look like this. And again, between these terminals, you would have 110 to 120. Okay, single phase plus single phase gives you two-phase supply. But now your total voltage is 120 volts plus 120 volts, 40 volts. Now your voltage has increased. So real life example, when someone comes to install a high powered hot tub in a residence or any place, the electrician, the licensed electrician, must take these two phases, combine them together, and lay out the electrical grid work, not grid work, electrical wires and cabling to obtain 240 volts. Okay, and that is what a licensed electrician has to do. And so we are going to simulate that in today's experiment in lab 3. Okay. What you're going to do is you're going to take your two power supplies. In this case, it doesn't matter which one you choose. You can choose 1, 2, or 3. The power supply is limited to 2 volts. Look at the circuit diagrams. Okay. If you look at the circuit diagrams, let me show that to you. Excuse me. Only 2 volts. Right, 2 volts. So it's 2 volts. This is how you're going to combine the two power supplies together. You have, let's see. These are the two supplies that you're going to use. Doesn't matter which one you use. You can use 1, 2, or you can use 2, 3, or you can use 1 and 3. Doesn't really matter. But you're going to take a short cable and you're going to connect it from the negative of the first supply to the positive of the second one. Positive of the second one is connected to the negative of the first one. And what that does is gives you 3 terminals. Of course, you can connect your cable physically at either one. Yep. All you're doing essentially is you're taking the second power supply and pushing its voltage level down. So if you have This is plus minus 2 volts, and you have another power supply with plus minus 2 volts between its terminals, and you connect the negative of the first one to the positive of the second one. All you're doing is you're pushing it down. The level between the two doesn't change. This becomes plus 2 volts. This becomes minus 2 volts with your reference in the middle at 0 volts. That's all it means. You're combining two phases together. You're combining two power supply lines together. That's all it means. So in the real life example, I stated 120 volts plus 120 volts. The combined effect is you get 240 volts between the outer two terminals. So here the effect would be you have 2 volts and you have 2 volts. You combine it together, you have 4 volts going from minus 2 to plus 2. Does that make sense? So physically on your power supply, you take any two pairs of terminals, you take a short cable, you connect the negative of the first one to the positive of the second one. On your circuit diagram, it states or it shows something like this. Right? This is plus minus, this is plus minus. And then you have the rest of the circuit. This is what, VA, I believe. Yeah. This is VA, this is VB. This is your center terminal. This is the common terminal that you just connected. So translating the circuit diagram to the physical power supply box, this would be VA, this would be VB. You would set the power supply exactly in the same manner. You set the current limit first. The current limit, I believe in the lab write-up, states, I think, 0.5 or 0.1. Oh, ask instructor for assistance. Set it to 0.5. Okay, set the current limit to 0.5. So set current limit to 0.5 amps. Then you set the output current also to 0.5. Then set the voltage to 2 volts, and then proceed with the experiment. Okay. So again, this is the first connection that you need to make. This is your one. Power supplies VA and VB. Choose any one of 1, 2, or 3. Doesn't really matter which one you choose. Okay. Whichever end is positive, whichever end is connected common, that is your common terminal. The other end is plus 2, the other one is minus 2. Okay. Now, let's take a look at the lab. So wherever it says, the model number, it's older power supplies, we don't use those anymore. And so ignore those, but you have to read everything else. Okay, make sure you read everything else. One very important point I would like to make is you note the directions of the currents right here. I1, I2, I3. When you break the circuit and you insert the meter in the middle to to measure these currents, now you don't have to do it for the first one because it's just calculated. But whenever you do, when you calculate or when you measure the voltage, you always keep the reference direction in mind. Okay. The polarity of the voltage that you're measuring has a plus on the left for R1. For R2, it's on the right. R3 is also on the right. So you keep those in mind. When you're measuring the current, again, the meter positive should be on the left and minus should be on the right. Plus on the left, minus on the right. If you don't do this, then you will note down the incorrect, you would be recording the incorrect value, incorrect sign. And when you sum it up for KVL and KCL, you would not obtain a balanced equation. Does that make sense to everyone? You have to ensure that you are connecting the meter according to the reference direction shown in the circuit diagram. Otherwise, your equations will never balance out. Okay. And that's one thing. The other one is calculated currents. You can simply calculate using Ohm's law. Okay. Calculated currents, use Ohm's law. So let me note that down in the lab notebook. Calculated currents, use Ohm's law. That's it. Then we get to procedures 2 and 3. You're going to connect. You will connect a high impedance load. Basically, you will connect a resistor 130 ohms. Let's see. No, not 130. 100 ohm. This 100 ohm resistor is simulating the hot tub. You are connecting that 100 ohms in parallel across both the power supplies. Okay, that's the high energy load. That's what we are simulating. And once we have that, again, you're going to measure the upper loop voltages, which is power supply A, the lower loop voltages, and then you calculate the currents again with Ohm's law. And here's the third part where you verify superposition. Okay, when you verify superposition, you will, again, principle of superposition states if you have multiple sources in the same circuit, you can analyze a circuit with only one source active at a time, measure or calculate the currents and voltages, and the sum of both together should give you the actual voltage or current, right? So in this case, in this circuit, you have supply A and supply B, VA and VB, something similar to the pre-lab. VB reduced to 0 means you disconnect VB from your circuit. All you have to do is you take that cable out. Okay, you disconnect it from the circuit. And in its place, in the place of VB on the circuit, you're going to connect this node to R3. Okay, you're going to connect that node to R3. And that's what it means to reduce VB to 0 for the circuit. Okay, do not short out the actual power supply. In reality, it's very straightforward and very simple. You mark the cable which says VB, you take it out of the power supply, and you plug it on the circuit directly to R3. That's it. It's two birds with one stone, so to speak. You remove the cable from VB, from the actual power supply box. You now disconnected VB. That's the first goal. And the second one is creating a short. You take that open end and you plug it directly into R3. And that's the second part. So one simple action gives you two results. Does that make sense to everyone? And then when it comes to VA, you do the exact same thing. VA is disconnected, only VB is connected. So you remove VA from the power supply, the cable that is VA, and you plug it in to R1. Again, two results with one action. Does that make sense to everyone? I hope you all are taking notes. You're not? Okay. So that's reducing the voltage supplies to VA and VB to 0. Now, when only VA is connected in the circuit, all the three currents that you measure I1, I2, and I3 will have an additional subscript of I1A, I2A, and I3A. Okay. So upper source is VA and lower source is VB. So let's see. Upper source is VA. Lower source is VB. So the currents measured with VA would turn to I1A, I2A, and I3A. When only VB is connected and VA is disconnected, you measure the same currents again. So you have I1, I2, and I3, but this time the subscript would be IB, I2B, and I3B. And the actual value of I1 is I1A plus I1B. Same thing for I2, same thing for I3. And that is what you would verify in table number 3. Okay, that is what you would verify in table number 3. You would have the measured values for I1A, I2A, I3A. You'd have the measured values for I1B, I2B, and I3B. And then you'd have I1, I2, I3 from table 2, calculated values from table 2. You would compare the measured values with the calculated values from the top. And that's how you will verify superposition. And again, as I was stating, when you do these measurements, you be very, very careful in how you are connecting your meter. So let's begin. I'll leave you to our own devices. Open up the Excel sheet. I have them open at my end. As you collect your data, I will verify. I will also walk around the room. If you have any questions, just let me know and I'll come over. Yeah, make sure you measure your resistor values before you begin, and then do all the calculations using the measured resistor values. Okay. Again, you can use LT-Spice to do your calculations. You can do manual calculations as well as LT-Spice simulations. Either one is fine. So that's a very good question. So if you're doing LT-Spice, the ground should be at the common terminal because that's your point of reference for everything. Let me announce that to everyone. Everyone, if you are just for your not just for your information, I mean it's important. The common terminal between the two supplies would be your reference terminal. That's your common terminal for everything. Okay, so if you're doing LT-Spice simulations or you're doing any calculations, the common terminal between the two, which is basically right here, this common terminal is your reference terminal. So in LT-Spice, you would put the ground symbol, or you would connect the ground to that common terminal. Make sense to everyone? Okay.